Good afternoon, everyone. My name is Tristan Lijsbeth. I'm working for the Laboratory of Geotechnics and Monitoring of the BBRI, the Belgium Building Research Institute. And I'd like to welcome you to our fifth workshop webinar on distributed acoustic sensing this time. This webinar is organized in the framework of a project monitoring of structures and elements with optical fibers, which is supported by the Flemish Agency for Innovation and Entrepreneurship. And the project partners of this project are KU Leuven, the Structural Mechanics section, and the Division of Geotechnics, Structures and Concrete Technology of BBRI. All information about this project is available on the project website, ovmonitoring.be. And it's the aim of this project to promote the use of optical fiber sensing in the Flemish construction world. So the program for today, I'm very happy that today we were able to bring together 4 experts in the field of distributed acoustic sensing. We will start with an introduction to DAS technology by Sergei Mikhailov, a postdoctoral researcher at Brussels Photonics of the University of Brussels. Followed by Thijs Lankriet from Fluves, who will present their solutions for leak detection and corrosion monitoring with DAS. Then we also have Corentin Caudron of ULB, who will be presenting how they use DAS technology for monitoring calderas and glaciers. And finally, we have Raúl Escorihuela from Aragon Photonics. So that's a manufacturer of DAS devices, who will end this webinar with some more DAS applications. Your questions, you can ask them via the chat of the Teams session. We will try to answer them at the end of each presentation. And yeah, of course, please turn off your microphone during the presentations. Of course, you can turn it on if you have any questions after presentation. And this webinar is being recorded and will be put available after the webinar online. All previous webinars are also available online. You can find them on the BBRI YouTube channel or on the ovmonitoring.be website. And I already mentioned it, but more information about optical fiber monitoring is available on the project website, or you can just contact me. So I propose to start and pass the word to Sergei for the first presentation and an introduction to DAS technology.
Well, yeah, thank you for the introduction. Well, I am not quite a postdoctoral researcher yet. Just we'll have to wait for a couple months for that. So yes, no problem. Yes, my name is Sergei Mikhailov. I am a PhD researcher at the Brussels Photonics Department of the Vrije Universiteit Brussels. And yes, now I will give a brief introduction into distributed acoustic sensing. So DAS is an optical fiber sensing technique, and optical fiber sensors feature some unique advantages over traditional electronic and electromechanical sensors, such as they have low weight and small size, which means they can be minimally intrusive. They're made of glass, which means they're chemically inert and immune to electromagnetic interference. They are passive, which means they can be remotely interrogated without the need for local energy supply. They are sensitive to multiple stimuli, such as strain, temperature, electric current, pressure, and so on. This, well, sometimes can be a disadvantage when we talk about the cross sensitivity between different parameters, for example, cross sensitivity between strain and the temperature. And which is very important in the context of this webinar, they have a great multiplexing capabilities. So how fiber optic sensors work. So the light is propagating in the optical fiber, and it is modulated by a certain measurement of interest, temperature, pressure, or something else. And this measurement changes some certain parameter of the light, such as intensity, frequency, phase, or polarization. And this measurement is encoded into this parameter of the light. So fiber optic sensors, in terms of number of sensing points, can be separated into three classes. The first is a point sensor, where you have just one discrete measurement space, for example, with the fiber Bragg rating. The point sensors can be combined into an array or quasi-distributed sensor, where you have several sensing points interrogated by one interrogating device. And finally, you have a fully distributed sensor, where you have continuous measurements along the whole fiber length, which is the case of distributed acoustic sensing. So distributed fiber optic sensing market is rapidly growing and expanding. So for example, the average annual growth of fiber optic sensing markets exceeds the average economic growth in the respective countries. So which means that it is really quite booming technology. And nowadays, distributed temperature sensing has the largest market share, and distributed temperature sensing is primarily used in oil and gas industry, but also for structural health monitoring, for example, for tunnel, power cable, and transmission line monitoring. Distributed acoustic sensing, in its turn, is also rapidly growing and soon approaching the distributed temperature sensing. And the number of companies that exploit this technology is also growing. So here is a selection of the companies that provide interrogating devices, but also just a fully integrated sensing solutions. So distributed sensing is based on light scattering in optical fibers. So there are two main types of light scattering, elastic and inelastic. So inelastic scattering happens with the change of the light wave of the light. And Raman and Brillouin scattering are the types of inelastic scattering. So there are many commercial devices that are based on the Raman and Brillouin scattering, and they're mostly used for quasi-static and static measurements, whilst distributed acoustic sensing makes use of the Rayleigh scattering, which is elastic scattering process, and this means that it happens without the change of the wavelength of the light. So Rayleigh scattering is caused by the microscopic density fluctuations on a scale that is much smaller than the light wave of the incident light, and in our case, it is the wavelength is around 1.5 micrometers. So the light is partially scattered in all directions, and a portion of light is gets backscattered and trapped into the fiber again and propagates back into the launching end. And so the DAS makes use of this backscattered light. And well, in distributed acoustic sensing, the fiber optic cables are interrogated with the short laser pulses, and while the light travels through the fiber, it's continuously backscattered, and the position along the fiber is then can be retrieved by the time of flight of the optical pulse, as you can see here. So the principle is quite similar to a one-dimensional radar. So you send a short light pulse, it comes back, and you yeah, pretty much listen what happens in the fiber. So you detect this backscattered signal, and it looks like this kind of noise-like pattern that forms so-called fingerprint of the fiber. And this fingerprint is unique for each fiber, and it is static in time when no perturbation occurs. But this pattern will locally change when you have some perturbation in the fiber at that position. And in case of acoustic sensing, so acoustic wave propagates through the medium surrounding the fiber, and then when it reaches the fiber, it stretches and compresses it. And this causes local change of the scattering pattern at this point. And this lies in the base of the simplest intensity detection DAS. So this is the scheme of the experimental setup. So you have a laser, which is, well, the laser light is chopped into pulses. These pulses are then amplified and injected into the fiber. And then the backscattered light is detected by the photoreceiver. So you make consecutive measurements into time instances, and then you compare the backscattered profile, and if there is some perturbation, some vibration in a certain location, then by comparing these two traces, you can see the difference. And the main advantage of such measurement is of such technique is that it provides single shot measurements. So with every light pulse, you get a new measurement. But the main disadvantage is that the changes of the backscattering profile do not linearly depend on the amplitude of perturbation, and the sensitivity of the measurement varies from point to point. So pretty much you can locate the perturbation, but you cannot definitively say what is the amplitude of your vibration. So you have a qualitative measurement. To have a quantitative measurement, one of the solutions is to detect phase of the backscattered light. So while when the light propagates through the fiber, its phase linearly increases with the position, and it also linearly depends on the applied strain, as you can see in this figure. So for example, when you have vibration at a certain position, then the phase will linearly follow the applied strain. So we have linear measurements, and also in schemes with the phase detection, sensitivity is uniform along the fiber. So one of the popular schemes for the phase detection DAS is so-called dual pulse DAS, where you interrogate the fiber not with one, but with two pulses with slightly different frequencies. So you generate a pulse pair that is amplified and then launched into the fiber, and then you detect a differential signal between these two pulses, which looks like this. So it has this sort of jaggedy form, and the phase of the signal linearly depends on the strain. So you detect the phase of the signal and you have a linear measurement. Another interrogation scheme is so-called chirped pulse DAS, is when you inside the interrogating pulse, frequency is linearly scanned, linearly tuned, and in this configuration, the backscattered trace, when there's some vibration, this vibration causes temporal shift of the trace, as you can see here on this graph. So by comparing two measurements, you detect this temporal shift delta t, and then from there you can retrieve your strain measurement or the temperature measurement. So the short pulse DAS provides linear and quantitative measurements. So the data in DAS is typically represented in form of waterfall maps, where the acoustic energy or the phase changes or already retrieved strain changes are represented as a function of time and distance, and the event intensity is shown in the color. So for example, in this figure, you can see 3 events separated in time. So next, some key specifications of the DAS instruments, the spatial resolution, which is typically defined by the pulse length, and it is usually on the meter scale in the commercial devices. The next is acoustic sampling frequency, which is defined by the length of the fiber or the time that it takes for light to go to the fiber ends and back. Next, the maximal sensing length, which is defined by the energy of the interrogating pulse. And finally, the sensitivity. So in modern quantitative systems, it is usually on the level of nanostrain in terms of strain and vibration, and millikelvin in terms of temperature changes. So as I already mentioned, the distributed acoustic sensing is growing fast with new applications emerging every year. So, and mostly the DAS is used for seismic sensing, for oil and gas exploration, intrusion detection, asset monitoring. The main driver for industrial use of DAS is oil and gas industry. And so there it's used for in boreholes for seismic profiling, flow monitoring, and leakage detection, and also in the midstream sector for pipeline monitoring. The DAS is also used for monitoring of the civil infrastructure, for example, railroads. In this example, the DAS is used for train monitoring. So with just a standard telecom fiber that is placed in the cable ducts next to the railroad, it can detect the noise coming from the train wheels, and with this you can monitor the train traffic and also, for example, derive the speeds of the trains. Another fascinating example is the earthquake detection with DAS. So in this study, the researchers used a DAS array located next to the Belgian coast to detect a deep earthquake next to the Fiji island, so which is more than 16,000 kilometers away. And here you can see the comparison of the signal recorded with the DAS on top and the seismometer, and here in different frequency bands. So as you can see, the DAS signal, yes, it is a bit noisier, but still it's very fascinating how sensitive it is and how it can detect from almost half the globe away. And finally, in the recent few years, a combination of DAS with machine learning and artificial intelligence has become a very hot topic. So there, machine learning is used for event recognition because, well, DAS provides enormous amount of data, and the machine learning is used to select these events, and this combination allows envisaging different smart city applications, for example, for road traffic monitoring and control, and gas and water leak detection, and of course more about applications from our next speakers. So finally, some takeaway messages. So the DAS exploits Rayleigh scattering within regular optical fibers. With each year, number of application increases, and it attracts more industrial players in rapidly growing markets. So these interrogation systems, yes, they might be expensive, but the specifications, for example, the sensor length over 100 kilometers with just a meter level spatial resolution, are not achievable with any other technology. And the possibility to exploit already installed telecom fibers also greatly reduces the cost per sensor. So that is it from my side. Thank you very much for your attention.
Thank you, Sergey, for this theoretical introduction to DAS technology. Very interesting. I would like to ask Thijs Lankriet to share his screen. He will present us two solutions from Fluves, a Belgian monitoring company for leak detection and corrosion monitoring with DAS technology.
Okay, so I'm going to go a bit more into the practical applications of DAS, also for structural health monitoring. First, a quick word about Fluves. So we are an engineering company that is based in Ghent, working especially on fiber optic sensing. So not just DAS, but also DTS and other fiber optic sensing applications. We do not build the interrogators ourselves. We use interrogators from different suppliers and use them to fix clients' problems. So if a certain contractor or industrial producer has a problem in their process, we use fiber optic sensing to solve their problems. And we do this mostly in the markets of pipeline monitoring, power cable monitoring, river monitoring, and also monitoring industrial processes. So those are four different core markets. Today I will cover not two, but three different applications. The first will be monitoring pipelines for leakages and intrusions. This is our DALI product. The second thing that I will be presenting is detecting corrosion under insulation on chemical pipelines. This is our COI control product. And then as a quick encore, I will give also some information about monitoring offshore power cable protection systems, which is an application developed by our daughter company. So first, let's start with monitoring pipelines for leakage and intrusions. This is an image from a pipeline burst that occurred in 2018 in St. Peter's Leeuw near Brussels. This is a pipeline from the drinking water company Faris that burst and flooded several houses, so it caused quite some damage. That's why Faris contacted Fluvius to say, okay, we have this extensive network of existing but aging pipeline infrastructure that we'd like to keep in use for longer, but we'd like to equip it with a monitoring system that not only gives a permanent monitoring system or permanent monitoring, but also gives immediately the location of any incident such as a leak. And so based on this, we developed our DALI pipeline monitoring. Now, DALI consists of 4 different components. The first is the optical fiber. So we developed a special fiber optic cable that is compliant for use in drinking water applications, because in the drinking water sector, there are heavy regulations on what can come into contact with the drinking water. So we developed a cable that is suited for drinking water use. And we also developed an installation system that allows us to install this fiber optic cable inside the pipeline while it remains in operations. So there are different, that's a big added advantage because that means you can retrofit existing pipelines with your fiber optic cable. Then the second important component is the DAS optical interrogator. So this is what we are talking about today, of course, and that what Sergey extensively introduced. Then the third part is the software that analyzes the DAS measurements. So from the DAS comes raw measurements of the deformation of the fiber. So you can think of it as having a microphone inside the pipeline every 10 meters. Then our software recognizes any sounds and detects sounds of interest, for example, a leak or an intrusion or an excavator which can come into close contact with the pipeline and then detect these important sounds. And the fourth part is an online dashboard which gives to the client the status of their pipeline at their fingertips, allows them to monitor their assets 24/7. And this dashboard also includes alarming. This figure or this slide shows DAS measurements in action on a pipeline. So here we have a fiber optic cable inside this pipeline. And here on the top right, you see one of these waterfall plots that Sergey was also referring to. When the operator here opens a valve on the pipeline, you see here an immediate response in the signal intensity on the DAS. So it shows you both the location as well as the time of the disturbance. Now, these are still the raw measurements that don't tell you exactly what the signature is of the leak. So with the DAS, we have all the frequencies that we can analyze. So based on that, we can do sound recognition and tell the difference between, for example, a leak or another event of interest. So what the client gets is not these raw data, but they get a simple and user-friendly dashboard. This is an example of such a dashboard that shows a map of the pipeline. It shows also the sound level, so it shows you which places on the pipeline are louder. And then here, for example, when we create a leak, some dots on the map are colored in red, showing an alarm. And also immediately in the sound level plot, you can see a new peak has arisen in sound level. So this allows you to pinpoint the leak with an accuracy of 10 meters. Of course, not every peak here in the sound level is a leak because there are other sources of sound as well. And so this is where our sound recognition software comes in to tell apart a leak from any other acoustic event. What do we use DALI for? It can be used for all different kinds of pipelines, mostly water trunk mains, so the large transport pipelines, but also for water distribution pipelines. It can also be used for district heating networks and other networks such as industrial or sewage pipes. An important advantage of DALI is that it can be used on any pipe material and any diameter, because in water leak detection, there is a big problem with monitoring plastic pipes, because when you do an acoustic leak searching on a plastic pipe, any leak sound is damped by the plastic pipe. But our technology is not affected by this because our fiber is in the entire pipe, so it's also right next to the leak, which means that damping is not an issue. How do we typically deploy DALI for a client? There are different formulas. The most common one is to do a permanent monitoring. So in this case, we install the fiber inside the pipeline and leave it there forever, and also connect the DAS that sits there permanently. And this means that the client gets a 24/7 monitoring service that can alarm whenever there is a leak for the next 20 years, for example. This is, of course, best suited for critical pipelines, such as large diameter transport pipelines. And there are already quite a few of these transport pipelines in Belgium. So this is definitely a very important use case. Now, as Sergey said, the most important cost element in the hardware here is the DAS. So for less critical pipelines, sometimes it does not make sense to purchase a DAS. So in that case, it's also possible to place a fiber optic cable, which is very cheap, inside the pipeline and leave it there permanently. And then connect it to a DAS periodically, for example, every 6 months or every 3 months, to do a pipeline health assessment. So for that, you can lease a DAS from us, or you can also purchase a DAS and then move it between your different pipelines. Then the last application is short-term leak detection. So in this case, when there is a leak on a small pipe, which cannot be found with any other technique, we come in, we insert the fiber optic cable, we find the leak, and then we retract the cable again, and everything is back to normal on the pipeline. Here are some pictures from a case study that we did with Varis. Varis is one of the largest drinking water suppliers in Belgium, and they had us install 6 kilometers of a pipeline between Asse and Dilbeek with the DALI monitoring system. We've been operationally monitoring this since October of 2020, so for over 2 years now. Varis has conducted several blind tests in which they generate a test leak by opening a valve, for example, without telling us. And we've always been able to detect this whenever this occurred. This slide shows some images from our installation system. So this is how we are able to install cables inside pipelines without any without taking out the pipeline out of service. So by doing this, you can equip your pipeline with fiber without interrupting or with minimal interruptions, and this also allows you to use the fiber for other purposes. Okay, so that was my first application. The second application that I'd like to discuss is monitoring corrosion under insulation. This is a bit more of a industrial application than a structural health monitoring application, but I think that there are still many contractors that are actively working on these industrial sites, so I think it's still of interest today. Within the petrochemical industry, about 40 to 60% of all pipeline maintenance costs are due to corrosion under insulation. It's really a huge problem in the industry, and that's also why there is a huge demand for better monitoring solutions. Now, what is COI exactly? On chemical plants, there are many pipelines that transport heated materials, such as chemicals or hydrocarbons. In this case, you have a pipeline, for example, typically a steel pipeline. Then there is an insulation layer, which could be rock wool, for example. And on the outside, you have a cladding, which is often made of aluminum. Now, if the aluminum cladding on the outside is not completely waterproof, then moisture can enter the insulation, and this can lead to very rapid corrosion on the steel pipe because the steel pipe is heated. So these are really ideal circumstances for corrosion. So it can go very quickly. right here you can see a video of one of these installations that we took at a real industrial site. So you can see that, yeah, it can really absorb quite a lot of water and cause quite some corrosion. So for this, we developed another monitoring solution called COI control, which uses a combination of distributed acoustic sensing and distributed temperature sensing to monitor COI. We first validated this technique together with Series within an Interreg project, and this is a picture of our test setup. So you have here different small cladded pipelines with a fiber optic cable on the outside that we use to monitor for COI. Now these pipelines or these pipes were equipped with holes on the top, and then water was inserted in a controlled way to monitor moisture ingress and also corrosion risk and even corrosion itself. So then when we did these tests, here are some results. So the green line here shows our COI indicator on pipeline section that was dry. The orange line shows a pipe section in which 5 milliliters per hour of water was infiltrated in a controlled manner. And the blue line shows 80 milliliters per hour, so a very wet installation. And you can clearly see the results or a very strong response on our COI indicator. That means that not only our COI control system can detect moisture, even at very low moisture levels, but it can also quantify any or the corrosion risk. And so it can make the difference between a high corrosion risk and a low corrosion risk. Now, how does this work in practice? An important part here is that you want to retrofit to existing pipelines. There are already many kilometers of pipes on production facilities, and it's mostly the existing pipes that are vulnerable to corrosion. So an important aspect of COI control is that it can be done by placing the optical fiber on the outside of the pipeline. So all you need to do is tape it with a special tape or glue on the outside of the pipeline, and so you don't need to dismantle the pipeline in order to start up COI control. Again, what we provide to the client is not any raw data or an Excel sheet, but we provide them with an online dashboard that allows them to monitor their assets in real time and also get an alert whenever a new spot with corrosion risk is detected. So this is an image from an example dashboard. And then here are some images from a case study that we did at BASF, so the chemical plant in Antwerp. There we equipped about 300 meters of a heated pipeline with COI control. After a few months of measurements, we detected 3 different points of interest. Then BASF did a visual inspection without dismantling anything, which is one of their standard monitoring and inspection protocols that they follow. And on these 3 spots, they did not observe any damage to the outside cladding. So with a normal visual inspection, they would have not spotted anything unusual. But then several months later, we removed the cladding and we inspected the insulation, and we did find corrosion risk, such as you can see here in these pictures, on this pipeline. So that means that we are able to detect corrosion risk even at a very early stage, and we can also localize it. This system has a resolution of 1 meter, and also these validation tests at BASF in a real case show that in each case our localization of the corrosion risk was spot on. So we're able to find which places need to be repaired. Then the last case application that I would like to present is monitoring cable protection systems. And so now we are moving to the offshore wind world. And this is an application from our daughter company, Marlinks, who also uses DAS. So in the case of an offshore wind farm, you have an offshore high voltage substation And then you have inter-array cables, which connect a string of wind turbines to the high voltage substation. Now, most of these inter-array cables are trenched below the seabed, but where you have the transition between the monopile foundation and the subsea trench, the cable has to come out of the seabed, and there it is protected by a cable protection system. Now, this is really a critical part of the offshore wind farm, because if this cable fails, then all of these wind turbines can no longer make money because they can no longer bring their electricity to land. So this is really important. And to underline this, last year, or actually in 2021, the news came out that Ørsted, which is one of the largest offshore wind developers in the world, had to write off almost $500 million on their balance sheet because of problems with the CPS systems. So this really sent a shockwave through the offshore wind world, because such a big damage case is really quite a big figure for a young industry like offshore wind. So these CPSs were really recognized as an important part, and so again, advanced monitoring was necessary. So here, in case there is a problem with a CPS, there are several mechanisms that can lead to failure. Either if the CPS comes in free span, it can start swinging and therefore cause fatigue on the cable, or it can scrape over the scour protection, which is a rock layer placed at the bottom of the monopile. This can then lead to scraping and also damage. So here you have a picture of some tests that we did at scale. So monitoring a real inter-array cable with real CPS systems to detect or to generate the scraping. And then similarly, we also did some free span swinging. So this, if you have this 20 years, you will get fatigue and damage to your cable. So then we monitored this with us, and these are the results. So this is, in this case, a graph showing frequency on the x-axis and signal intensity on the y-axis for a single point. So here at the scraping location, and you can see a factor 3 difference in the signal. So that means that we can very clearly detect this type of abrasion, which is very important for monitoring purposes. When you have a cable swinging in free span, you not only get a very clear increase in the signal intensity, you also get very distinct peaks at the free span frequency. So this allows you to get the eigenfrequency or the swinging frequency, which is important to estimate the free span width and also any fatigue risk. So when you have these measurements, of course, the power of DAS is that you have spatial measurements. So you have them every 10 meters, and you also have permanent measurements. So you can start interpreting this measurement output in both space and time. And this graph shows results for a single spatial position as a function of time. So here you can start relating your signal energy to, for example, the metocean conditions, so waves, wind, and so on. Then also see how much the cable was scraping or swinging or both. And you can also do the same thing in space, and so identify locations which are more at risk or less at risk. And so you can start prioritizing your maintenance or your mitigation schemes. So those were 3 practical applications that I wanted to show about distributed acoustic sensing. Now, it is clear that these type of fiber optic technologies have strong advantages over classic inspection methods. I think the most important ones for the structure or the construction industry are, first of all, that our monitoring systems are continuous. So instead of doing manual inspections, which are a snapshot, you have permanent measurements. And so with an inspection, you can have, if you have a new leak occurring 5 days after the inspection, you will not see it until you do the next inspection, which could be 1 year later. The second is that it's location aware. So any incident is not just detected, but it's already immediately located with a high accuracy. And it's also autonomous. So all that you get is a dashboard, and you don't have to do manual inspections anymore, or you can optimize your existing manual inspections by looking at prioritized locations. And so by doing these types of monitoring, you can save operational costs. You can monitor, for example, the health of your installation or the health of your pipeline, and thus reduce energy costs, water leak costs, but also maintenance and inspection costs. And you can also extend the lifetime of your assets. Of course, we all like to build new infrastructure, but the reality is that, especially in Belgium, we have a lot of existing infrastructure that we should keep in life for as long as possible. This is the most economical option usually. So equipping existing existing assets with monitoring systems allows them to keep them in use for longer, while keeping the risk of incidents at a low level. And so for this, we also designed our systems, both DALI as well as CUI control, for maximum retrofit capacity. That means that existing insulated pipelines can be retrofitted by equipping a cable outside of these pipelines. And for underground pipes, you can use cable that goes inside the underground pipeline. So that was a bit my story, but I'm sure that there are many more other applications. And so when we talk to clients, we often discover new problems where fiber optic sensing could be the best solution. So if you have any questions, we are always available to talk either now or after this webinar. Thank you.
Thank you, Tess, for these nice examples. Are there any questions for Tess? Okay, I don't think so. So then we can continue to Corentin Caudron of ULB will present us. Hello. Hi, Corentin. Here is a question. Sorry. From Glenn Thiers, are manual inspections completely replaced by the monitoring at BASF?
That really depends on the application. And I cannot comment on what BASF is going to do there, because that's their decision. And I also don't want to disclose all of their operational practices. But it's clear that by doing these types of inspections of monitoring, you can indeed greatly reduce and also greatly optimize your inspections. It's not always about, okay, we want to reduce our inspection team from 6 people to 3 people, but you can also just keep using the 6 people to find issues faster and more efficiently.
Okay. Are there any other questions? Okay, then Corentin, it's up to you.
So, well, I'm going to present something a bit different. There's a bunch of people that have been helping me with this thing, including people who are here today. So I'm not going to detail their names, etc. But yeah, it's a massive effort, and I'm going to focus on monitoring volcano calderas using fiber optic cables, and I will give you a bit of background because that's probably needed when it comes to volcanoes. So the main motivation for, let's say, this project in general was to see whether we could sense volcanic gases using fiber optic cables. And the reason why we are interested in these things is that volcanic gases are the main trigger of explosive eruptions. Yet the largest amounts are actually emitted through passive degassing. So when the volcanoes are not doing any eruption, so during quiescence. The challenges we face, well, we have many, but one of them is that it's difficult to detect volcanic CO2, so carbon dioxide, which is a major gas when it comes to volcanic gases, because as you know, there's a lot of CO2 in the atmosphere, which is not volcanic. And as a result, the global estimates will vary widely from 66 to 540 megatons per year. The other problem is that the volcanic gases are experiencing, when they are released from the crater, turbulent interactions and dilution in the atmosphere. And in that case, even the ideal subaerial volcanic tracer, which is SO2, so sulfur dioxide, is difficult to relate to source processes. So that's the problem we face in the atmosphere. So the idea was to to go underwater. So this is not new because we know that there is a strong acoustic impedance contrast between gas bubbles and water. So I'm going to show you a few examples first, which are not related to DAS technology, but which give rise to this idea of using it in volcanic settings. So this is an example of a lake which is in Indonesia, Kelut Volcanic Lake. You see its usual color, it's blue, so there's no problem when it's blue. And then sometimes it turns to yellow. And then sometimes there are eruptions, as you can see here. There's a dome, so lava dome, which was erupted during the 2007 eruption. So it changed. This volcanic lake changes a lot. So as I mentioned, the cool thing is that the bubbles are easily detected in several volcanic lakes. It's something we've been doing for more than a decade now, and we use hydroacoustic approaches. So basically what we do is that we sail on a boat, a small boat, because those lakes are usually quite remote, an inflatable boat, and then we were using echo sounders, because echo sounders will emit waves in the water. When you have a target, which can be the bottom of a lake, for example, bottom of the ocean, that's what you see here as a white line. The echoes are reflected back to the transducer, but that also works with bubbles, and in that case, sulfur spherules, but we don't really care about sulfur spherules in this talk. The cool thing is that then we can try to quantify or at least characterize the degassing areas. And that's what we've been doing for years now. And this is very useful because in the case of Kelut volcano, so getting back to Kelut, the volcano with varying colors, you can see that in general, the flux of CO2 derived from different techniques, including Cassander, was around 30 tons per day. So every year we were going to the lake. I was not there, I was still studying in 2002 and 2003. But my partners, my collaborators were going there and said, well, everything is fine, it's 30 tons per day. And then suddenly in 2007, just a few months before the eruption, the emissions were multiplied by 10. So they recorded 3,300 tons per day, which is of course a bit concerning. So they thought there was a problem with the instrument, but in fact it wasn't a problem with the instrument, it was a problem with the volcano. And the cool thing for us, or at least we think it's cool, is that this started 2 months before any seismicity, any deformation in the volcanic structure, which is the main thing we are looking at when we do monitoring of volcanoes. So this would be a very early precursor to the eruption that occurred 4 months later. And so it means that essentially if we are capable of sensing the CO2 using hydroacoustic techniques, we could be doing a better job in terms of monitoring. So that's what happened to the lake. So the lake was there, and while you see the situation later, 4 months later, there's no lake anymore. There's just a lava dome that fortunately was emitted passively, so there was no big explosion in the volcano. So building up on these ideas, we thought about new ways to quantify and not to only characterize degassing, but to quantify passive volcano degassing in aquatic settings. So we did a few tests where exactly it's close to Belgium. It's actually very close to Belgium. It's close to Koblenz, to Köln. So it's the Eiffel volcanic zone. And more specifically, there is a big lake which is called Lagersee volcano, which hasn't erupted for more than 12,000 years. So it's at the geological scale, it's yesterday. So it could erupt at some point in the coming years. But it hasn't erupted for more than 10,000 years. So it's quiescent, and that's what you can see here on the left side of the photo. It's a very nice lake, and there's no problem currently. The cool thing for us is that there are many bubbles. So we've been using this site as a way to test new techniques, and it's a very convenient site to carry out multidisciplinary works. But since the last years, we know that the volcano is actually not that quiescent. So there are movement of magma that are kind of triggered around 30 kilometers of depth, and there's an uplift which is centered around the volcanic area. So it's we don't know whether it's the volcano itself or the entire zone which is uplifted, so which the ground is moving up, but it has been moving up in this region for the last 20 years. So this raised, of course, interest from a volcanological point of view, because we don't only want to test new techniques, but we also want to do monitoring now. So I'm going to show you first a few examples, again, not related to the task, but just to show you how I usually look at bubbles underwater. So that's an echogram, which means that it's an echography of the lake carried out with a CPIX, which is an instrument from X-Blue. So it's just a fancy echo sounder. And we see fish. We see the bottom here, and then we see trains of vertical echoes, which are actually bubbles. This is in very shallow areas, so like 25 meters of depth. And this is a map we created with all the profiles we could do with the echo sounders. If that works, there is a video where we used the CPIX, so the standing echo sounder, in a static mode. It doesn't work. Well, no big deal. You would have seen bubbles which are rising towards the surface. And this is cool because then we can monitor the gas flux in real time, or at least that's what we would like to develop in the future. Now it works. So the echoes you see here are actually bubbles that are rising towards the surface, and their sizes are decreasing when they are rising up, which is for us a way to interpret that is that we have gas dissolution, CO2 dissolution in the water column. Then what we have been using is also hydrophones. So hydrophones are just passive microphones that you put in the water. And what you see here is a spectrogram. So it's just a fancy word for the frequency on the y-axis, the time on the x-axis, and you have the energy as colors. So when you have lots of energy, you have, let's say, yellow-green colors. When there is no energy in terms of frequency, you have blue colors. And what you can see here is during 7 hours, we have continuous energy around 1000 hertz, 750 and to 300 more or less. So there is a continuous activity in terms of bubbling with dominant frequency that you can actually relate to the size of bubbles through an equation which is called Minard's equation, which was first used or published a century ago. And we also have discontinuous bubbling, which means that bubbles are suddenly released close to the hydrophone, and they have again a characteristic dominant frequency that you can see here, which again we can relate to the size, which is very useful. And that's just with a hydrophone, so just one sensor located in a specific area of the lake. So that's how it looks like from the sea drone perspective. So the webcam in the water, you see the bubbles, you see the fish. Something similar has been carried out in Yellowstone Lake in the US a while ago. So I've been lucky enough to get access to the data, and you see here a waveform of a bubble. And this is not a Fourier transform, it's a wavelet, but we don't care really about the details here. But what it tells you is that you have a wide range of frequencies that are excited close to the hydrophone. So we have high frequency in the kilohertz range, frequencies down to 200 hertz, and we have even lower frequency close to the hertz scale. So we have different processes in there. And the cool thing for us, for volcanologists, is that most of the waveforms, the wiggles you see here, are quite similar to each other, which means that we're looking at something which is quite repetitive in time. And I forgot to mention that, but this is just using 13 hours of recording. So it's quite short. The hydrophone was set up at, let's say, 90 or 110 meters, so quite deep in the lake. And we observed bubbles for 2 hours, only for 2 hours out of 13, which is quite interesting. And the conceptual model we came up with is that essentially the way it works is that first, below the surface, beneath the lake floor, bubbles will be nucleating and will, when they are emitted and reaching the lake floor, emit acoustic energy in between 1 and 40 hertz. And then you have much higher energy, which is much higher frequency, which is excited due to the resonance of the bubble. So first you have the very low frequencies, which are due to the turbulence. Then you have the cavitation, so in the kilohertz range. And then finally, when the bubble is released, it will oscillate when it's rising towards the surface at a frequency around 100 and 200 hertz, which is again characteristic of the size of the bubble. And finally, it will dissolve before or when reaching the water surface. And then you can do monitoring, which is my main goal. You can track those bubbles, estimate their volume with time. And here you see my monitoring setup in Yellowstone, where during 2 hours, I could record the bubbles, estimate their frequency, volume, etc. So that's what we could do. Okay, so that's a pretty long introduction, but that's quite important. Now, some first and very preliminary results we got with the DAS. So what we did in 2021, so a year ago now, a bit more than that, we deployed the first fiber optic cable here in Lakersee, so the lake in Germany. And you see it's a 500 meters cable, which doesn't float, so that's a good thing. It's that the cable went directly down to the bottom. We had divers who coupled the fiber optic cable to the ground to make sure we had a good coupling, because we are, of course, interested in seismicity. And that's what we set up during a few days. And what you will see here, hopefully on the left side, is the cable. So it's the blue cable here, which then is going towards the lake, and you will see a few bubbles. There's fish. And what I'm showing you on the right side is a characteristic waveform. We record it around the fiber optic cable. So we have one waveform at a given channel, so 135 meters away from the interrogator, and then we have another bubble. The same bubble recorded 6 meters away. So you see that the frequency is already different, and that's quite important for us and quite interesting. So then what we did is that we compared those recordings that you see here at the bottom in Lakersee. So we have 22 milliseconds of recording to laboratory experiments that have been done in the lab, of course. And you see the characteristic waveform they recorded with a hydrophone, and that's on the bottom recorded with a DAS, so with fiber optic cable. And you see that you have the waveform, which is high frequency in the lab, followed by a much lower frequency oscillation when the bubble is detached from the sediment and start oscillating. And so we were quite happy because we said, well, we have something which is quite similar to what we have seen in Yellowstone with hydrophone, in Lakersee with hydrophone, but also in the lab. And we can try to start interpreting those things as high frequency interactions with the sediments, so with the lake floor, and low frequency stuff which are related to the bubble briefing. And then we designed a template matching. So it's a fancy word for basically taking a waveform which is characteristic of the bubbles and going through all the data we have. So in total it's 500 gigabytes of data for 2 days. And we found out that we have around 11,000 bubbles which are quite similar, around a 30-meter section of the cable. So when the template finds something which is similar, it becomes red, and when it's not similar enough, it's blue. That's what you can see here on the right side. And on the upper left side, you have a spectrogram of the bubble signal. So frequency, time, and energy. When you have lots of energy, it's yellow. And the cool thing, so sorry about the figure here, it's just very new stuff we got last week. What we did with a PhD student based in the University of Michigan in the US, together with Zach Spica, and so his name is, the PhD student name is Yaolin Yao. We kind of try to track the bubble waveform evolution through distance, so through the different channels. So this is channel 140, this is channel 170, and you can see that the waveform first is arriving later in time at channel 170, and the frequency is evolving massively. So we have something which is around 1000 hertz and much higher frequency when it's going away from the bubble location origin. And this is just a spectra of each waveform. And then, of course, you can try to cluster those bubbles based on the waveform and identify different populations of bubbles using correlation matrices like this one. The cool thing when it comes to the DAS, so first it's really sensitive to bubbles, but we also have information at very low frequency, down lower than 10 hertz, which was a bit similar to the hydrophone, but seems to be more reliable with the DAS. So that's something we are actually now exploring more details because we think it's worth investigating more. And the last thing I wanted to mention for the Lakersee experiments is that there is also information at depth in the sediment, which is very important for us. So here you have an autocorrelation created for each channel of the fiber optic cable, and you see that we can see some structure which are indicative of things which are changing in the subsurface, possibly faults or possibly gas seeps towards the surface. So something again we are really currently exploring, and which we could relate to, for example, seismic reflection, which was carried out by Vlies and Ukent. Okay, checking the time, I still have a few minutes. I wanted to show you very recent works that we have done with Aragon Photonics and also Fluves to some degree, where we realized that we have some problems, for example, in the sea. So last month we went to Vulcano and Panarea in Italy, and we deployed hydrophones, HDAS from Aragon Photonics, echosonders, and geochemistry. So it's a nice work. We did it from boat. This is Stromboli, so it's not the worst place to work. And the food is excellent, as you imagine, in Italy, as opposed to Germany, which is not that great. And this is there's a black smoker, which you can see here, the black color. So that's quite rare, at these shallow settings. And this is an idea of how the hydrophone was set up. This is the ocean bottom seismometer, and here is the fiber optic cable in the bubble field. So there's a lot of bubbling in there. And this is the acquisition from the boat. So we tested the acquisition from the boat directly. We connected the HDAS for more than a day, and it worked very fine. No gap, nothing. So it's really cool. We'll get the data very soon, and we start working together on this thing with Aragon Photonics and Fluves. And we did the same experiment in Vulcano, where you have this geyser, you have the beach with people swimming around, which is a bit weird because it's a pretty dangerous area, but we did the same thing with the fiber optic cable laid out around this geyser-like structure. And we have a nice correlation between the frequency of the bubbles and the tides, which means that the water column is kind of changing the frequency and the radius of the bubbles. Okay, the last thing I wanted to mention very quickly is that we again did another experiment, but this time in Iceland, where we tried to deploy a DAS cable, but it failed. But at the same time, we tried to deploy a fiber grating through a collaboration with bsense. So there's the cable designed by bsense here with a Bragg defect located every 5 or 10 meters. And with this data logger, so the interrogator from bsense, which is in the box here, which has been working very fine for continuous monitoring purposes for the last 2 months. So it's quite successful, and we have both strain and temperature because we have in total we have 8 cables, but sometimes we have 2 cables located next to each other. And that's just a snapshot of the results. So you see here different Bragg defect, their wavelengths, and the wavelength shifts are quite intriguing. Just going to scroll because I have no time anymore to this figure where you see that you have a daily oscillation, which makes sense. The temperature of the ground, of the soil, goes down and increases during the day. But you have also those weird cycles that you can see here. It's an hourly 1 hour cycles, which we don't really understand right now. So we have to think a bit more about that. And the good thing is that I've got a PhD student to help me thinking and designing those nice codes. So here we have each channel, and the association is visible on each of those channels, which possibly are related to injection due to the power plant. So I'll leave it there. We have excellent and new data, so DAS is really a great opportunity for us. It's still a bit challenging for the monitoring perspective because we have loads of data, too many to be currently usable by people like me. So we need to come up with machine learning scheme and procedure. Fiber grating is a very promising alternative, but at a short spatial scale, and it comes with complication due to manufacturing of the cable. And I'll be happy to answer any question, of course. Thank you.
Thank you, Corentin. Are there any questions for Corentin? I think it's impressive to see how you can detect these small bubbles with DAS technology. It's maybe a special application to show today, but it might inspire people for other applications. I don't see any questions for Corentin. I do see another question, but was I think for for Thijs from Raphael de Smet. Is this the same like OTDR measurement? What's the maximum length of fibers? How many weldings in the fiber? I don't know. Tess, can you answer this question?
Yeah, I will answer it, but then Raoul, if you want to add, you're very welcome to, because I think it's also for the other speakers. So in one sense, DAS is similar to OTDR in the sense that you use radio scattering, but in another sense it's different because you use it to measure vibrations. So with a standard OTDR, you cannot measure if the cable is vibrating, and certainly not you can certainly not measure at which frequencies the cable is vibrating. Maximum length of the fibers. Commercial DAS devices go now up to 70 kilometers one way and 90 kilometers even with an amplifier. How many weldings in the fiber? Yes, this does affect your fiber, so it's best to limit the number of splices and also the number of connectors. That depends a bit on the application and on the device, but as Raphael says, a normal device has an optical budget, so you can work out which length and which number of connectors you can have by looking at the optical budget of the device. So, for example, yeah, if you have a device with let's say 8 dB optical budget, you know you can do so many kilometers and so many connectors and so on.
I think this answers the question of Raphael. Bram van Hoe.
Thanks. Yeah, just wanted to add a small comment. First of all, thank you for the very interesting talks. On the optical budget and on DAS systems, I just wanted to highlight that we at FBGS, we are making Bragg ratings. We're also making Bragg ratings specifically to enhance the backscatter signature of an optical fiber. And this can also tailor or amplify or modify the maximum length you can interrogate and also tune the sensitivity to a certain extent. So besides using standard telecom fibers, there are also options to combine low reflective specific Bragg ratings to enhance and tailor the response of an optical fiber in view of the DAS measurement system or auto-distributed measurement system you're using. So I just wanted to add this to the discussion. Thank you. Okay,
if there are no other comments or questions, then we can go to the last presentation of today. I'm happy that Raúl Escorihuela of Aragon Photonics, I hope my pronunciation is not too bad, wants to present us some more DAS applications just to end this webinar. So Raúl, you can share your screen and the floor is yours.
Hello. I want to briefly present you one of the projects in which we are working on. I'm in charge of part of the company that is working on applications for DAS measurements. In this case, we have been working for 3 years now, deploying a project that consists of the detections of vibrations in cable infrastructures. Our client is looking for possible threatening activities next to their cables that are energy cables, subterranean cables, and also they have two submarine cable sections that we are measuring also. The project started back in 2019. The 3 first interrogators, which are this Hector model from Aragon Photonics, which works. This is it's not an HDAS, it's a DAS based on coherent reflectometry. This is a excuse me, based on not quantitative, qualitative measurement of the strain. And it has 4 outputs to monitor 4 fibers. That's why it was selected for this project. But also we have installed 2 HDASes, not because of the quantitative measurement of the strain is needed or frequency characteristics of the signal, but because of the extended range of this equipment. The equipment that is installed already, it's located 2 units in Madrid, 2 units in Barcelona, 1 unit in Valencia, 1 unit in Gerona, in La Coruña, in Mallorca and Menorca, and another one in the Canary Islands. And the submarine cables are located in Menorca and the Canary Islands. In total, we are measuring 22 cable lines, and the cable length adds up to 500 kilometers of cable. All the interrogators are reporting alarms to a central server. We just give alarms to the end user. The supervisors of the cable infrastructure have this web application. They can access to it from any computer, and they have the alarms located on a map, and also they can interact with the alarms and acknowledge them. The system architecture we have developed for this is based on a server which receives the alarms from the 10 DAS devices that are now installed. For each new installation, we configure in the server, in the backend of the server, the new sensor and the cable route into the map, and the device gets the stimulus from the real world from the fiber. We have a detection software, and we extract events from the waterfall. These events have several features that we can measure, and in base of these features, we decide with another software if they are alarms that are compatible with civil works activity next to the cable. After we set up another interrogator unit, first thing we do is a mapping. So we have to walk many kilometers because each cable has tens of kilometers to make sure we are locating the length of fiber where the events are happening to the map correctly. After that, we call it zonification. The next step is to see how the waterfall looks like, because there are different zones of the city where not only the base noise that we are receiving from the fiber is different because of the activities that are going on there. Can be traffic, can be intersections, can be trains or subways, but also the sensing capabilities of the cable, the sensitivity of the cable is different from one place to another. So we have to take all of this into account to do a good discrimination of the sounds that can be compatible with civil works. After that, with all this information, we do some thresholding for the signal to be more or less sensitive depending on the zones. And here we have some examples of the waterfall. This is the raw data of the waterfall. This is in the city of Valencia. Here we have civil works going on in 2 places of the waterfall because the fiber is going and coming from the same street, and noise of cars, noise of people walking on the sidewalk, and several places where we have still noises also that are not noises but reflections of the signal that are permanent there. After the first step of processing, we get clusters, and these clusters have several features that we measure, and we take note of them to the next step, where we decide from different features of the signal if they are alarms or not. These alarms are logged into an alarm log and sent to the server, and in the server we present them to the end user. We have been working for 2-3 years in this project. We started with the client, allowing them to give us feedback from the alarms that we gave them. In the different places we have deployed the equipment, they have given us enough feedback to perfect the detection, and we are now giving them a very good rate of alarms that are truly civil works or construction works in the proximity of the cabling infrastructure. So this is my presentation. This is very short, but this is the last one. If you have any questions.
Okay, thank you, Raul. Are there any questions left for Raul? I see that there was another question from Rafael. No bidirectional measurements. Des or someone else, do you want to comment on this one?
To give a short answer, you only need one end of the cable. So connecting the DOS to one side of the cable is enough. There is no added value in the loop measurement, for example, what is done in.
Okay, I think this is clear enough. Okay, then I just want to finish this webinar. Thank you very much to all speakers for their time and their contributions. If you have any more questions about monitoring with optical fiber, please don't hesitate to visit the project website of the OV monitoring project, or you can just directly contact me and I can put you in contact with for example, the speakers of today or other companies. And just a small reminder, all previous webinars are available online. You can find them on the project website, but also on the YouTube channel of BBRI. So thank you very much and have a nice afternoon. See you later.